My dear students of CE806 Structural Analysis and Design of Concrete Structures 2 Sessional. Assalamu alaikum for the Muslim students and Adab for the Hindu students. In this course there are distinct two parts. One part is the bridge part, the other one is the building part. You must have a lesson, by this time you must have lessons on building part, but this is the first lesson on bridge part. I am Professor A.F.M. Abdurrauf. I will be dealing with this part of the course, and Mr. Hasibul Hassan will deal the other part. And so far I believe he has given 2 lectures on this subject, and my lecture is the third one, and I will be dealing with balanced cantilever bridge. In the previous course of CE804, you have learned about bridge design, and that was a simply supported girder bridge. And before that, you have learned about a slab bridge where no girders were used. And now we will go for a longer size of a bridge, and if the bridge span is increased, then the 2 supports will not be sufficient. In that case, the bridge depth, girder depth will be so big that that will block the waterway. So we will go for from 2 to 3 supports, or 2 spans, or 3 to 4 supports, 3 span. If we use 3 support and 2 span, the middle support will be at the middle of the water course, and that will is not very simple solution. That is not a wise solution, because at the dry season the middle support will make hindrance to the navigation, and that's why from 2 support we will be jumping up to 4 support, and in 4 support we will be having 3 spans, and the bridge will become a continuous beam bridge. And if we use 3 support, the middle support will be at the middle of the river, and that will, in the dry season, the navigation will be in the middle side of the river. That's why the intermediate pillar will make hindrance to the navigation. That's why, as I have said, we will go from 2 to 4 supports. That means 3 spans. And if we make this 4 support and 3 span, the beam will be a continuous one. And in our country, the river bed is mostly alluvial with alluvial soil, and there is the stability of the river bed is uncertain, and that's why we are very scared about this support condition and settlement and other things. So we will try to make the bridge is a simply supported one with cantilevers. If we use 4 supports and use cantilevers towards the middle part of the bridge, then there will be no support at the center of the bridge, and the navigation at the dry season will not be hindered, and that's why we will be using 4 support, and we will use at the middle one a cantilever, from 2 sides 2 cantilever, and to make the middle gap bigger, we will give another simply supported beam on these 2 cantilevers, and that will make the middle span bigger, and the navigation at the dry season will be improved. If we use only cantilevers, the middle portion will be smaller. That's why we will give from 2 sides 2 cantilevers, and the middle will support another simply supported portion at the end of these 2 cantilevers. In this way, we will make this balanced cantilever bridge, and we will be using 4 supports, 3 gaps, and the middle gap little bigger than the side gaps, because the middle gap will be required for navigation for all the year through. And in this way, we will go for a balanced cantilever. Balanced means the middle support, middle portion will be in such a way that it will not be so big and it will not be similar to the other spans. Normally, the middle span will be bigger than the side spans for navigation purpose, and there is a ratio, there is a relation between the the middle span and the side span. Normally, we keep the middle span 1.5 times of that of the side spans, and in this way the navigational part in the dry season at the middle portion will be little bigger, and that will serve the purpose at the dry season also. In this way we will go for this cantilever bridge. That means from the two end supports we will give protrude some cantilevers, and on the cantilevers we will be supporting a simply supported portion, and with these two cantilevers and simply supported portions the middle span will be bigger than the side spans. And for this we will use some data, and we will go through a rigorous calculation of this bridge bit by bit, point by point, and step by step. Now we will present the data will take for this design some specific data. With some specific data, arbitrary specific data, we will be designing the whole bridge, and this will be a sample calculation and sample size and sample type of bridge. Length of we will be taking some design data like length of the bridge 300 feet, Fy concrete strength, and Fy steel strength 60 ksi, F prime C concrete strength 3 ksi. FYT is the transverse reinforcement steel stress. That's here we have chosen that also as 60 ksi. Transverse yield strength of transverse reinforcement or stirrup. Normally we know as these as stirrups. And like building floor finish is there, wiring course will be casting some depth of the concrete for slab design, and over that we will be using some bituminous course, bituminous carpeting. That will the weight of that bituminous carpeting will be 30 psi. Standard lane width for one truck or one vehicle is 12 feet, and walkway we will be using here. Both sides we will be using walkway as 4 feet. There is about the width of the walkway. It depends on how the people will be walk through this bridge. If it is if there are many people, then we keep it as a wide walkway, or if there is little chance of pedestrians, then we can keep it to 3 to 3.6 inches. Now for this particular bridge we will be using 4 feet on both sides. And number of girders, here I have a specified number of girders, but there is a limit. The number of the spacing of the girders, store limit is spacing of the girders should not be more than 10 feet. And live loading will be HS20, HS15, HS20 loads. And the previous two bridge designs we have given you details of the loading system, and what are the wheels, where are the axles, and wheel load, axle load, etc. All these are given in the previous course, and you can go back to those notes for seeing what is HS20 loading and how the loads come to the ground from that truck. Semi-trailer truck, HS highway semi-trailer truck. This is S stands for semi-trailer, and in this vehicle there are two parts. The front part is the driving part, and the rear part is the load carrying part. That's why it is known as semi-trailer HS20. We will be giving detail of this while we will be designing or taking the loads for our design purpose. And now we will go for this solution. We have 4 lanes. As I have mentioned in the previous part, we have 4 lanes and 2 sidewalks or walkways. Then the cross width of this bridge is 4 lanes into 12 feet plus 4 into 2 walkways, that means 56 feet. Maximum spacing of girder is 10. If we use 6 girders, then the spacing of the girder is 9.33, that is 9 feet 4 inches, that is less than 10 feet. Therefore, this choice of this 6 number of girder is okay. Choice of the 6 number of girder is okay. And if we use less than that, the spacing will be more than 10, and if we use more than that, the spacing will be less than 9 feet 4 inches. Sometimes we can use more girders. In that case, the girder depth will be less. Here I have chosen just 6 girders and 6 girders, 56 divided by 6. As there is cantilever on both the sides, that is why I have divided it by 6. If there were no cantilevers, then we would have to divide it by 5, because the half cantilever on the right side and half cantilever on the left side makes another span. That is why I have made it divided by 6. If you see the figure, you will understand this better, why I have used here 6 spaces are there. Intermediate spaces are 5, and the half space in the cantilever and half space in the other side cantilever make the 6 spaces. That is why it is divided by 6, and the space center to center of the girder is 9 feet 4 inch, and that is less than 10, and 10 is the maximum, and that is why the number of girder choice is okay. Depth of girder normally taken as there is a limitation. It is not the ordinarily taken. If there is a limitation, the length of the girder should not be less than length divided by 40, and that is why I have divided this height of this beam as h, and ls is the length of the girder, because here I should have gone as the depth of the girder normally taken is length of the girder divided by 14. Here, as we have chosen the bridge as 300 feet, the end span is 60 feet, and the other end span is 60 feet, and middle span is 120. The figure is in the next page. The division of this support and the spans is on the next page, page 6. Anchor span. Depth of the girder normally taken is length of the girder divided by 14. We have chosen the exterior span of the girder as 60 feet, and if 60 into 12 divided by 14, that gives me a depth of the girder as 54 inch, and the end spans, because the end span is 60 feet. The middle span, as you have you know that this in the previous course you have designed a 60 feet bridge, and if you divide the 60 feet by 14 into 12, that gives you the 54 inches. This is the middle simply supported span depth, and width of the girder normally is in the range of h by 3 to h by 4. Here h by 3 to h by 4. If you divide this with 54 divided by 3 and 54 divided by 4 is in between the 16, then this is in the middle value is 16. That's we have used 16 as the width of this girder. 16 as the width of this girder, and we go to the next page. Here I have drawn a cross section of the bridge, half cross section. As you see, we have used 6 beams. That is why you have shown here 3 beams. We have shown the cantilever walkway on the left side. Then the curve height is 10 inches. This is a standard one. carve height is 10 inches. This is the standard one, you must remember this, and we have kept this 4 feet cantilever of the walkway. Walkway will have some railing, and total width is 4 feet, and the 54 inch, as I have decided earlier, the beam is 54 inch, and there are the spacing of the center to center of the beam is 4 inches, and from there if we deduct the beam width 16 inch, then the gap between beam to beam is 8 foot, and 7 inch slab, as you know, maybe you have learned in earlier courses that minimum slab thickness is 7 inches. Previously it was less than, it was 5.5 inches, and nowadays as the loads are heavier, then they have come to this 7 inch minimum thickness of slab. And this is the cross section, half cross section of a bridge, where simply supported span is there, and you have learned this sort of thing in 60 feet bridge, simply supported one, and this is the part of the simply supported one as the middle span, and other portion of the bridge will be different from this part, and they are near the support. As there is negative moment is more, we will be increasing the beam depth to certain extent, that will come later on. Normally the mid span is taken here. We have divided this mid span and end span with some relation. Normally the mid span is kept near about 1.25 times the side spans. This is from practical point of view and general style of this sort of relations. If L is the length of the side span, then total number of spans will be, if we call this middle span as 1.25 and two side spans are 1 and 1, then we have to divide this 300 feet by 3.125, and from there we will get L value. And the L value, after a calculation, we have got something simple odd number. Therefore, we have gone to a round figure of 90 feet. The value after revision is 92 feet. We have used this as 90 feet. 90 feet. The mid span. This is this L is for where the span is 1 into L. That is why the end span is, you see it in the bottom figure, the anchor span is 90 feet, and the middle span is 90 minus 90 divided 300 minus 90 plus 90 remains 120 at the middle span, and the middle span is divided into some cantilever part, and the simply supported 60 feet bridge, that is the 630 is the cantilever part of this anchor span, the left span, and the middle portion is the simply supported span on the cantilever. This is supported by the cantilever end on both sides, and this is 60 feet, which is the equal to the girder bridge we have learned previously, simply supported 60 feet span, and the right cantilever is 30 feet, and another, the last span is 90 feet. We have shown part of this long section here. That is, first of all, the anchor span is 90 feet. From the anchor span, a cantilever part will come out about 30 feet, and from the other side there is another 30 feet, and total mid span is 120 feet. This 120 minus 30 gives us the middle span as 60, which is similar to the bridge we have designed in the previous course. Slab design. The slab design procedure is similar to the slab design of the simply supported bridge, because that is why we will not repeat the slab design in this course. In CE806 and you have learned this slab design. So, we will come with the interior girder design. We will go directly to the girder design. And if you have learned about the diaphragm in the simply supported beam design, you know that there are some cross beam like things in the bridge, those are called diaphragms. Beam to beam, long beam to long beam, the cross beams are there. Those are not called beams because they will not carry direct vertical load or from the wheel. They will act as a strut between these two long beams, and these are placed at 30 feet spacing across the long beam direction. And as there are 90 feet in the end span, there will be two diaphragms as two supports and two intermediate diaphragms at the middle. There are some specifications that the diaphragm dimensions, there is some the minimum width of diaphragms at support is 16 inch. Supported at the supports, the diagram specification says that the width of the diaphragm will be 16 inch and depth of the diaphragm will be equal to the depth of the beam. And now, here we have to know what is the depth of the beam. We got 16 inch from the specification, and here the depth of the beam is 54 inches, and 54 inch minus the 7 inch is the slab thickness. That is why if you have to divide it by 144 and multiply it by 150 as unit weight of concrete, and the diaphragm's length is 8 feet, because we have the center to center, the clear spacing of the beam is 8 feet. The clear spacing of the beam is 8 feet. That is why we have multiplied this by 8, and the load comes to 6267, and it is rounding with 6.3 kip. We have kept it as 6.3 kip. Factored value, because we know this dead load factor for bridge design is 1.25, not 1.2 as in building design. Here we have to use the factor 1.25 for bridge design, and our normal load is 6.5 kip. That multiplied by 1.25 is equal to 7.9 kip is the diaphragm load at the end span. The intermediate diaphragms will be of lower width, smaller width and smaller dimension. That is, the intermediate diaphragms are kept as 10 inch wide, and depth of the diaphragm is less than the 12 inch less than the main girder. These are kept smaller than the depth of the main girder. That is why here, first of all, we have put this 10 inch, the width of the diaphragm, intermediate diaphragm, and beam depth is 54. That minus is 12. 7 inch is the minus 7 inch is the slab thickness dimension, and minus 12 is the specification dimension of 12 inches. And this multiplied by 150 into 8, because the clear span of this diaphragm is 8 feet, and we have multiplied this by 8, and this comes as 2.9 kip. Here 8 is the clear length of the diaphragms. I have written it like this. Factored value is 1.29 into 1.25 is equal to 3.6 kip. That means the intermediate diaphragms, weight of the intermediate diaphragms is 3.6. These are concentrated load at the specific points, a specific distance of this beam. diaphragms for interior support. Here for the beam we have normal beam we have kept the depth as 54 inch, but at the interior support where the some cantilever will be coming out, and on that cantilever the middle span will be supported. The intermediate beam depth must be much bigger than the left support or right support beam depth. At the interior support where there will be a cantilever, and that cantilever will support a simply supported span to make the middle gap bigger. Then that is why the cantilever will have a heavy load from the simply supported reaction and its own weight and own load. That is why we will keep the intermediate portion of the beam bigger than the normal beam depth, as we have taken it previously as 54 inches. We will take it as about 1.5 times 54 inch, and that is 81, and we will keep it as a round figure 82. Now, factored weight of middle support diaphragm. We are calculating the diaphragm weight. It's 1.25 is the load factor, dead load factor, 16 is the width, and 82 minus 7 is the depth of the diaphragm. 7 minus goes for slab, and that divided by 144 into 150 is the unit weight of concrete, and 8 foot is the length of this diaphragm from out to out of beam, and that is 12.5 kip. This much. Now we will slab weight. Self weight of slab is 7 is the 7 into 12.5 is 30 psi. 30 psi is the wearing force, and 7 into 12.5. 7 is the thickness, and 12.5 is the per inch thickness weight. That means slab weight per square foot is 87.5 psi per square foot, and wearing force is 30, and total is 117.5 psi. Factor load for this one is again multiplied by 1.25, as in dynamic load we use this 1.25 as the factor load for dead load, and it is 1.47. Load per feet of slab to beam is 17.5 into 9.33. 9.33 is the center to center spacing of the beam, and that gives a load of 1097 factored. You have to use the factored value 1.2725 into 1097 is equal to 1372, and we have kept this as rounding the figure to 1.4 kg per feet. Factored weight of beam stem. The factored load of beam stem is 1.25 is the factor dead load factor for bridge design. 16 is the width of the beam. 54 is the total depth of the beam minus the slab thickness, and that divided by 144 and multiplied by 150 gives us a value of 980, and that is equal to 0.98 kg per feet. And total dead load is for the beam, as we will not be going to the design of slab, we have come here direct to the beam. The per running foot of the beam, the slab load will be from its stem weight and 1.4 kg, and from slab weight, stem weight is 0.98 and slab weight is 1.4 kg. Total is 2.38 kg, and that is shown here in this span. The bridge, almost half of the bridge is drawn here. The left arrow shows the left support, middle arrow shows the middle support, and the some cantilever portion is extended from the middle support to 3, and the diaphragm loads are shown as concentrated load, the left support at the middle point, another middle point 3.6, another middle point 3.6, and at the interior support where the beam depth is increased, there is 12.6 kip load, and at the cantilever end there will be 3.6 kip of diaphragm load, and at the middle of this 60 feet span at the center there will be a diaphragm, and the diaphragm load will be 3.6, and the other diaphragm load is 3.6. We will be designing the bridge for this 60 feet span, which we have done in the previous course, but this will have some influence on the left cantilever part of the bridge. That is why this will be coming frequently from load from the simply supported span will be coming to the cantilever end, and this will influence the design. And with this we will be finishing for today's lecture, and if you have any problem you can phone me anytime from morning 8 to 10 in the night, and
অফিসিয়াল টাইম যেটা ঠিক করেছে ওইটা বলেন, সকাল 9টা থেকে কটা পর্যন্ত?
আমি বলি 9টা।
ঠিক আছে,
Thank you very much.